So if I give you this equation, right, how would you prove it, and what even is it? Well, this is the inverse of a matrix using its adjoint. And in layman's terms, this is another way how you can find the inverse of a matrix with just the determinant and its adjoint. But what good is an equation if we can't prove it, right? So let's start with that. So let's say we have the coefficient matrix times the adjoint of the matrix. If we were to perform a matrix operation for any of the rows and columns, for example, this row times that column, we would get the following product as any standard matrix multiplication operation. So if I was equal to j, what does that mean for the sum? Well, it simply means that the sum is the cofactor expansion of a in its ith row. And what does that sum end up being? It turns out the sum ends up being the determinant of a. Now, if I wasn't equal to j, that'd be a different story. So, now that we know that the multiplication operation for the entries will yield the determinant, let's rewrite this expression. So here is the operation rewritten with respect to your determinants, and we know that matrix A is invertible. Well, we have to assume matrix A is invertible because we need the determinant, and in the equation, the determinant happens to be in the denominator, so once again, that reinforces the point that it cannot be 0. So what do we do with this exactly? Well, let's see here. We have A times the adjoint equal to determinant A times the identity matrix. So let's divide both sides by determinant of A. And what does that look like exactly? Well, I'll show you guys. So this is what it looks like when we divide both sides by a determinant. And if we were to divide both sides by the coefficient matrix, with it being A, that would end up looking like this. Where we have 1 over the determinant times the adjoint of the coefficient matrix, and the identity matrix over the coefficient matrix is simply the inverse of that matrix. And there we're now able to prove that the inverse of the matrix is equal to 1 over the determinant times the adjoint of the matrix. Now that we have the proof down, let's execute with the more numerical example. Okay, so this is the given matrix. The determinant ended up being 3. You can deduce that answer via your calculator or by, well, I prefer to expand by the second row since there's a 0 there. And the transpose is basically your matrix of cofactors, but transposed. And to find the adjoint of the matrix A, you take the cofactor of each entry within the original coefficient matrix, and you take the transpose of the matrix of cofactors. That's how you find the adjoint of the matrix. Go ahead and pause that video and work it out yourself. And in the meantime, I'll jump straight to it. So by referring to the equation we have just proved, given that we have the adjoint and determinant, this is just a matter of distributing the 1/3 into the adjoint, which ends up looking like this, where we have 4/3, 1/3, 2/3, 2, 0, 1, 7/3, 1/3 and 2/3. Okay, and this is equal to the inverse. Now, I'm going to leave you guys one homework assignment, and that is to double check our inverse. So we know that a times a to negative first power, which is the inverse, is equal to the identity matrix. We have just solved for the inverse, and in order for the inverse to be correct, if we multiply both sides by the coefficient matrix with the inverse we have, does it enforce the fact that this equation is true? Go ahead and confirm that.